Welcome to our poster presentation. The title of our presentation is Evaluating Arabian Peninsula Extreme Weather Ensemble Forecast Simulations at Convective Permitting Scale and Subseasonal Time Scales. This is a collaborative work between the University of Arizona and the King Abdullah University of Science and Technology in Tual, Saudi Arabia. Mesoscale convective system, or MCSs, over arid region, such as Arabian Peninsula, generate the most extreme rainfall and weather-related catastrophic hazards. Heavy rainfall over a short period of time results in fast-flowing surface runoff, leads to raging rivers and flash flooding. It often causes fatalities and damages in infrastructures. Though forecasting and weather analysis have been improved in the past years, there has not been study on subseasonal predictability of the AP extreme precipitation events through convective permitting modeling. The goal of our research is to improve forecast capability at subseasonal timescale for convective extremes in the Arabian Peninsula. We selected 21 extreme events during winter near Jeddah from 1999 to 2018. The criterion for our extreme events is any precipitation event that records daily precipitation total greater than 18 millimeters. This winter extreme precipitation is typically associated with intense extratropical systems. The modeling tool we use for the simulation is the Weather Research and Forecast Model with 20 and 4 kilometers resolution nested domains. The inner domain is convective permitting. The physical configuration is following Yesubabu et al. 2015 and the operational KAUST high resolution reanalysis. The forcing comes from ECMWF S2S reforecasts with 11 ensemble members. The simulation of the events is initialized at 1, 2, and 3 weeks ahead of the events. To verify the forecast skill and predictability, we use GPM iMerge version 6 precipitation product as a ground reference. We have compared the RMSE of GPM relative to the rain gauge measurement over the AP with the RMSE of the other satellite products. It turned out that GPM has the lowest RMSE. Statistical analyses are conducted to quantify the forecast skill of the simulations. The two that we include in this poster are probability of detection, or POD, and receiver operating characteristics, or ROC curve, and its quantification, the area under the curve, or AUC. The verification is within the spatial resolution of the original ECMWF on the order of 100 kilometers. Following Luong et al. 2020, we classified the events based on the synoptic patterns into 3 groups: extratropical, transitional, and tropical. The patterns are shown in the center figures in the poster. We apply this classification in our analysis. There are 10 events in extratropical, 3 events in the transitional, and 8 events in tropical patterns. Now the results. For the POD analysis, we compare the CP-WRF POD and the raw ECMWF POD with various precipitation thresholds, 5, 10, 15, 20, 25, and 30 millimeters relative to GPM precipitation products. They are all consistent that the CP-WRF exhibit precipitation improvement even in the higher thresholds. Here on the top center, we plot the POD difference between the CP WRF and the raw ECMWF for the precipitation events associated with extratropical patterns. The precipitation threshold is 20 millimeters. We see the results from 3-week to 1-week lead times. Rainfall improvement marked by positive values from the CP WRF persists out to 2 and 3 week lead times over the Red Sea and near the Persian Gulf. The area with positive POD are regions often receive higher convective precipitation. On the lower center is the figure of POD difference between the WRF and the raw ECMWF for the precipitation associated with tropical pattern. We have the results from 3-week lead times to 1-week lead times. And again, we see rainfall improvement marked by positive values from the CP WRF persisting out to 2 and 3 week lead times over the West Coast and Central AP. On the top right is the plot of the rock curve of the CP WRF for all events, and the lower right is the plot of the rock curve of raw ECMWF for all events relative to the GPM precipitation product. We find that 90% of the no-scale raw ECMWF forecasts improve to some reasonable scale in CP WRF out to 3-week lead time. We see here that many of the event curves have higher area under the curve or AUC greater than 0.5 in the CP WRF. When we classify the events into extratropical and tropical classes, we also see the same results. We calculate the AUC improvement of the CP WRF by subtracting the raw ECMWF AUC from the CP WRF AUC and then take the average. The results are shown in the lower right tables. Here we see all positive values in both the precipitation with extratropical and tropical patterns from 1 week to 3 week lead times. In conclusions, regions of precipitation improvement from CP WRF depends on the dominant synoptic patterns. 90% of the no-scale raw ECMWF S2S reforecast improve to some reasonable scale in CP WRF with AUC greater than 0.5 out to 3 week lead time. Thank you for your attention, and now I take questions.